Hello, everybody. Wait, actually, hold on. Let's see. Let's get to lab. Hello, my name is Melvin. This is lab 3, where we determine a black hole mass, and I build a unique orbit in code. In this lab, we determine the two forces. Well, we determine the forces acting in the two-body system, and we figure out the mass of the black hole. How? It's a good question, and I'll get into that later into the video. The initial velocity required to create a unique orbit for a spaceship traveling through a planetary system. That's the second part of this experiment, and I'll also detail how I figured this one out. The fundamental physics principles that we're working with today, we're going to start with velocity. We're going to move over to momentum, force, and then from force we'll be able to figure out the mass of the black hole. And we do this by using Newton's second law, which relates the change in momentum to the force applied. And because the only force present is gravity, we relate this force to the universal gravitation equation, which is right here. The preview of our results, the lab results indicated that the mass of the supermassive black hole is 1.35 times 10 to the 44th. That's 44 zeros after 1.35. This is derived by taking the average of 443 iterations, which I put into an Excel sheet and averaged out. The initial velocity for the spaceship to make a unique orbit in the three-body system is -500, 200, and 0. And notice that there is no z component. This is because the system is being observed with the z-plane parallel to the screen. For the first part of the experiment, our system is the star and the black hole is the surrounding. And in the second part of the experiment, the system is the rocket ship, and the surroundings include the moon and the planet. What does this all mean right here? Well, we're given the velocity by a unique key, which we then convert into momentum with the given mass of the star. And then we calculate the change of momentum over time. We also calculate the parallel component of the momentum, which is this part right here. That's the p hat variable, and then this is the d magnitude over dt. And those two, when you multiply, give you the parallel component of the change in momentum. And then with the parallel component, we subtract the total change in momentum. We subtract that from the total change in momentum to get the perpendicular component. That completes the code, but the only part we're really interested in is the F net line, because we substitute that into the universal gravitation equation to determine the mass of the supermassive black hole. And this is pretty much it. We have the universal gravitation equation here, but it's just rearranged so that everything else is on the right side, while on the left side we have the mass of the black hole. Over the many iterations, it was 1.35 times 10 to the 44. These chunks of codes evaluate the forces acting on each object in the second part of the experiment with variable systems and surroundings. It just depends on which one you're calculating for. I use these over each iteration to determine where each body would be to calculate the trajectory of the ship. Then I experimentally determined the velocity of the ship. This is what the code runs for the first part of the experiment, and this is what the red code runs for the second part of the experiment. Something really important to touch on here is what's the difference between force and what's the difference between the change of momentum. While numerically equivalent, the force and the change of momentum over time are separate by what they actually infer. The change of momentum over time is derived from observing the motion of the star over time. The force is actually the pull/push between the two objects. One is basically observing the change of motion of an object, and the other determines the strength of the gravitational force between two objects. And then, in order to predict the motion of the entire system, so that would include the black hole, star, planet, and moon, we would have to calculate the forces acting between each pair of mass bodies. In the situation we had at the beginning of the experiment, we only had to find the force between the black hole and the star, which is 2 forces. For the entire system, we have to calculate the force on each object, which turns out to be 12 forces. And that's really it for this lab experiment. Don't forget to like and subscribe, and ciao.